How do we look at the motion of things that are elastic? That is to say, how does a elastic force, that is energy built up in potential energy stored up by compressing or elongating something that will oscillate, how does that affect physics and motion? Well, if you're interested in such things or studying this in a class, stay tuned for this intuition video today from High Peak Education. What's going on, everybody? Thanks for joining me, and in this video what we're going to do is we're mostly going to focus on springs. A spring is a good example of an object which undergoes simple harmonic motion. That is, its motion is going to be governed by a linear restoring force, that is by Hooke's law, and a spring demonstrates elasticity. Now, even though we'll be mostly focusing on springs, you can imagine several other things display elasticity. You could imagine when you jump on a trampoline. If you weigh it down more, it stretches further down, and when you jump higher, it sort of goes back upward. So there's a lot of things that have elasticity. But the easiest one to model, the easiest one to describe mathematically will be a spring. Of course, there's lots of applications of springs themselves. That is in terms of shock absorbers, say on your automobile, or maybe shock absorbers in a building if there's a potential earthquake, things like that. So we're going to be focusing on oscillatory motion, simple harmonic motion, energy stored in springs, and also Hooke's law and elasticity. So let's dive into some of these things. So in our first experiment here, what I have today is a spring where I can set the spring constant and I can set the applied force. What I can show is I can show the applied force vector, the spring force vector, and the displacement vector. I can also mark where the equilibrium position is. The equilibrium position, by definition, is the unstretched position of the spring. So let's see what happens when I stretch this spring with a certain applied force. So this is kind of what you'd expect. Okay, so notice that I'm applying a force now of 50 newtons. Note the spring constant. The spring constant is 20 newtons per meter. That is basically a measurement of how tight the spring is. So that's going to be the force per length. That is to say, it takes 200 newtons of force to stretch this spring 1 meter. So that's an indication of how stiff the spring is. It's another way to say what I just said. Note that the applied force, being 50 newtons, when you apply it to this spring, should move this thing, I believe, 1/4 of a meter. Let's think about why that is. Well, if it required, let's say, 100 newtons, that would be half a meter. So 50 newtons would only be 1/4 of a meter. So let's take a look at that. Note, the displacement vector here is positive. That is, it's to the right on a positive x-axis. And the idea is that we're elongating the spring. We're storing up elastic potential energy. And notice something, though, that the applied force is also to the right. That's from the lever here. But what about the spring force? What do you think should be the direction and the size of the spring force? Pause the video if you need to. So welcome back. It should be to the left and of the same size. That is, we have static equilibrium here. The sum of the forces in the x direction are equal to 0, and the velocity is 0. So we have an equilibrium situation. Notice that when we have these two forces added together, one is a positive force, one is a negative force. Notice also the displacement and the applied and the spring force are proportional to one another, but they're also going to be opposites of one another in terms of their direction. But again, they're going to be proportional. How do I know that? Well, if I apply twice as much applied force, the spring force is twice as much, but the displacement is twice as much. Now, Anytime something that's brought back towards equilibrium that has a so-called linear restoring force, that is, it's proportional to the displacement, that is by definition what we mean by a force that is part of a simple harmonic oscillator. As we will see, since the restoring force, the Hooke's law spring force, is linearly proportional to the displacement, we'll see here that the spring force is going to give rise to simple harmonic motion. Now, by the way, let me go ahead and also investigate what it means to have a tighter or stiffer spring. Let's make the spring constant now 400 newtons per meter. So the spring is twice as thick. Now, by the way, I'm not sure if you can see it here, but if I make the spring even thicker than that, can you see that the thickness of the spring just looks more massive? And not so much massive on the spring, but it definitely looks tighter, it looks more substantial. That is to say, this is definitely a stiffer spring. Well, if we're at 400 newtons per meter, again, that's going to be a stiffer spring than 200 newtons per meter. So at 400 newtons per meter, we have a stiffer spring. So what do you think should be the applied force to get us back to 1/4 of a meter? Well, I think that should require our entire 100 newtons of force. Notice, to only go 1/4 meter this time, we are going to require 100 newtons of applied force. Since the spring is stiffer, the applied force required to elongate or compress that spring is larger. Okay, so as the spring constant, let's say, goes up, so let's go back to, let's say, 50 newtons here. As the spring constant goes up, notice that the displacement is going down compared to this applied force, and that's because you don't need as much displacement to have this large of a spring force. Another way to say this is that if you have a very large Hooke's law spring constant, if you apply a greater force, you won't have as much of a displacement because, again, the spring is tighter. Tighter springs with larger spring constants for the same force undergo less displacement. So now let us investigate what the actual kinematics looks like here, along with the forces, so a little bit of dynamics, for a mass on a spring on a frictionless surface. So let's see what the results of this Hooke's law is in terms of motion. So what I have shown here is an example of a particular spring and a particular mass on a frictionless table. Now we know that frictionless tables don't really exist, but let's just go with it because we're ignoring the effects of friction and air resistance for now. And this spring is producing a Hooke's law spring force on this mass. That is, this force brings the mass back towards equilibrium. That is, x equals 0. Notice that the initial position of this mass is to the right of equilibrium. That is, x is positive. Notice this spring is going to stop being elongated and it's going to start to compress and overshoot this x equals 0, which is the equilibrium position, and it's going to go to the compressed position. After being compressed, I think it's going to come back out and have a Hooke's law spring force that pushes it to the right. What we're going to do is we're going to plot that x position as a function of time. So this is like kinematics, position versus time. But notice what the shape is going to be. It's not going to be anything we've seen earlier in the course. It's going to be a wave, namely a sinusoidal wave. And when I say sinusoidal, I don't mean a sine function. I actually mean a oscillatory wave that follows, in this case, I think, a cosine function. How do I know that? Because x begins at its maximum value. At time t equals to 0, notice that the position is maximum, and we also know that the cosine function usually starts at its maximum value for the horizontal axis variable being 0. So I believe this is a cosine function with a certain amplitude. The amplitude of this cosine function is going to be the initial x position, which is not necessarily 1 meter. Usually the traditional cosine function has an amplitude of 1, but this could be maybe 0.25 meters. So then maybe 25 centimeters, who knows? But again, frictionless table, Hooke's law of spring force, linear restoring force, we should see this harmonic or sort of simple harmonic oscillatory motion. So let's go ahead and start and see what we observe. Force. So it is indeed oscillatory motion that follows a cosine curve. Let's examine. When the spring is maximally elongated, the Hooke's law of spring force is maximum magnitude to the left, bringing it back towards equilibrium. When the spring is maximally compressed, the Hooke's law of spring force is maximally to the right, pushing it back towards equilibrium, which again is x equal to 0. Notice that, indeed, the spring is moving what? At 0 velocity when it's fully elongated or fully compressed. And notice that it's moving at its maximum speed when it moves through equilibrium. Notice that there's a couple ways you could think about this. You could think about when it's completely elongated or completely compressed, it's all potential energy, no kinetic energy. Whereas when it's moving through equilibrium, it's all kinetic energy, no potential energy. Another way to think about this is that look at the position versus time graph. What is the time derivative at, say, when we're fully elongated or fully compressed? Well, the derivative of x with respect to t is going to be 0. That's because we have a horizontal derivative. And another way to think about this is that the velocity, by definition, at those points is also 0. Okay? So this is kind of what we expect for simple harmonic motion. Okay? By the way, notice that there's a certain frequency in how often this happens, and there's a certain period, that's a certain time, between these peaks and troughs. Now, by the way, the period is the time for one full oscillation. What if instead we wanted to start the spring at, let's say, equilibrium? So if we wanted to start the spring at equilibrium, but wanted to have it move to the right at first, we could grab this curve and, I have to reset it, but I could grab this curve and, yes, move it like that. Now notice, think about what's going to be going on here. Notice that, look at the derivative at this initial point at time equal to 0. The derivative of x versus t with respect to time is positive. That means the velocity is positive. This block should be moving to the right. When we get up to maximally elongated, then the velocity will be 0 again. Now notice this curve looks a lot more like a sine curve. So you could model this as the position versus time is sine of omega t, where omega is the angular frequency. We'll get to that later. Notice the amplitude, that is how far this thing stretches or compresses in terms of its magnitude, will not change. But also notice that, again, if you wanted to strictly model this as a cosine function, we're taking this cosine function and we're, in some sense, moving it to the right to get us to this new time equal to 0 point. So when you shift something to the right, I think that would be a phase angle shift of, listen to me, pi over 2 radians. Why pi over 2 radians? Because this is a quarter period in time space, and that should be pi over 2 radians in radian space. Because in radian space, we have to oscillate through 2 pi radians for one full oscillation. So you get the idea that in this case, I think phi, and phi is going to be the phase angle shift. Phi is equal to negative, sorry, I said that wrong. Phi is equal to positive pi over 2 radians. And remember, when you shift something to the right, That is to say, the curve actually has a, there's actually like a minus in the equation. So this is going to be like cosine of omega t minus pi over 2. And hopefully that makes sense to you, that we have to go a little forward in time. So in other words, omega times t needs to have the value of pi over 2 radians to get back to the original 0 point, to get cosine back to its maximum value. So if we start this up here, notice that we just start with the object going through equilibrium. Of course, other possibilities exist. We could start this not as a pure cosine function, but maybe as a pure negative cosine function, as maximally compressed, and then start this up. But notice that that's just a phase angle which shifted this, instead of shifting it to the right, pi over 2 radians, it shifted it to the left, pi radians. So I think this would be cosine of omega t plus pi radians. And again, that shifts it to the left with that plus pi radians. And notice that we could start this thing anywhere we want. We could set phi, which is the phase shift, to be, I don't know, we could shift it to the right, just like, say, pi over 4 radians, and just start it right there. I mean, that might be not as useful. But let me just say, the most common choice for a mass on a spring, frictionless table, is going to be a pure cosine function with phi equal to 0 radians. In other words, the most natural place, even physically, to start this mass with the spring is to start it maximally elongated at its maximum positive value for x, and then release it. So this is how we model simple harmonic motion. Now let's take a look at this in a little more detail and compare some interesting things in terms of amplitude and mass and spring constant and so on. Now what I have shown here is a test for 2 identical springs, 2 identical masses, but we can set their initial positions differently. Let's set the initial position of the first mass to, I don't know, let's call it 20, whatever that means, maybe 20 centimeters. So that would be 0.20 meters in SI units. And let's set the initial position of the second mass to 40 centimeters. Now notice, not surprisingly, given what we've said before, the Hooke's law spring force for the second mass, starting off, should be twice as large as the Hooke's law spring force of the first mass, because twice the elongation, twice the Hooke's law spring force, with the same spring constant, that is, the same stiffness to both of these springs. And also, for simplicity, let's assume these are the same masses, and again, frictionless tables. So what do you think? Which should take longer to complete an oscillation? Should the smaller stretch, the greater stretch, or should it maybe be the same? Pause the video if you want to think about it. Okay, I hope you're interacting with these videos, because you shouldn't just wait for me to do it and for me to explain it. You should try to think first, maybe why, and then see if your intuition matches what the result is. And it turns out they will have the same period and the same frequency. Now you may say, wait a minute, that doesn't seem right. Well, indeed, the second mass will move further. But even though it moves further, it has a greater force. So, greater displacement, greater force, same time for the oscillation. Let's watch this. And hopefully you see, indeed, the oscillation period and the oscillation frequency is exactly the same. That is, I think they actually move through the equilibrium position at the same time. Now, even though they move through the equilibrium position at the same time, the second mass moves through with a greater velocity. That is to say, the second mass had more elastic potential energy stored up, and so it has a larger kinetic energy, thus a larger speed through equilibrium. But the time and the period, same, and the frequency should be the same. Let's see if we can see this a little bit more drastically. Let's make the second mass 75 centimeters. And let's make the first mass just maybe 10 centimeters. And let's see if the time of oscillation is indeed the same. And we still have the same frequency and the same period. So interestingly enough, the period or frequency of a mass on a spring system is independent of the amplitude. Because greater amplitude means greater spring force, but a greater spring force over a greater displacement, the time of oscillation is indeed the same. Let me show one more demonstration of this, and then this time I'm just going to show this amplitude effect as it relates to a position versus time graph. So what I have shown here is basically the same thing, except we're going to allow this mass on this spring to oscillate vertically. Now, by the way, when we oscillate things vertically, in reality, on Earth, there's no way we can avoid the gravity force. So it turns out that let's just ignore the gravity force. Let's imagine that we're, let's say, looking straight down on this. Let's imagine the positive x direction is downward. And let's imagine this is a mass on a horizontal table, okay? Again, with no friction. So let's do a small amplitude oscillation at first, and let's see what the period is. That is the time of the oscillation, okay? If you watch it, hopefully you see that the amplitude is the distance from equilibrium that we first stretched it, or the distance that it compresses. So the amplitude is kind of like the number out front of the cosine function as this thing oscillates. Whereas the period is the time it takes from peak to peak or trough to trough, the time of one oscillation. And for this particular spring with this particular mass, it's 2 seconds. Notice, let's reset this, and now let's do a large amplitude oscillation. And what do you think is going to happen? Well, hopefully you know by now it should be the same period. We have a larger displacement, but a larger Hooke's law spring force. And indeed, in the absence of friction, this is what we see. So same period, larger amplitude, but the same frequency and the same oscillation time. Okay? So this is what we mean by that a spring that is frictionless with a mass attached to it has its period and frequency independent of the amplitude. Now, it turns out if we do change the nature of the spring and the mass, things will change, but we'll get to that here very soon. But let me show one more example, this time comparing two masses, but starting them off with different velocities. And so indeed, this is how I've set up the experiment. Again, a comparison of two equal size masses, two identical springs, but this mass having 2 meters per second for its initial velocity, this mass having 4 meters per second. Do you think they're going to have any difference in their frequencies or their period? I hope you say no. But again, the second mass should have a larger kinetic energy because it has a larger initial velocity. Okay? So it doesn't look too different from when we compared the masses before. So even with different initial velocities, we see that really it's the properties of the spring and the mass itself that's going to determine the period and the frequency of the oscillation. Let's in fact investigate that now in a little more detail. And so what I have shown here is another mass on a frictionless table with the same spring constant we had before. So let's call it about 1, and let's just say that's units of newtons per meter or so. And let's initially set the velocity to 0, and let's give it a modest initial position, maybe 40 centimeters, okay? So I'm going to set it. Notice that this is its initial position, this is its initial spring force, and let's let it oscillate. And notice that it undergoes simple harmonic motion, which we've seen before. Now, question is, what if I wanted to set this up to have not a pure cosine function, but a pure sine function? Well, I think I should give it an initial velocity, but no initial position. So you can imagine if the object's moving to the right, at first, it should go up in terms of it should be moving in the positive x direction before it stops, and then to the right. So let's set its initial velocity, I don't know, maybe let's make it 6.4 meters per second, who knows. And let's start it, or sorry, I have to set it, and then start. Okay, so notice this ends up being a smaller amplitude oscillation than what we had before, because there was more energy in elongating this about the 40 centimeters than giving an initial velocity of 6.4 meters per second to the right. So this is a smaller amplitude oscillation, but you see that the frequency and the period is the same as before. Okay, so let's reset. Now let's do something a little more interesting. Let's go ahead and change it so that the spring constant is double what it was before. Now what do you think should happen? Okay, so hopefully you paused the video and thought about it, but basically the idea is that there should be a larger Hooke's law spring force. So if I have the same displacement that we had before, that is the initial position is 40 centimeters, notice that with double the spring constant, we should have double the Hooke's law spring force. And what do you think is going to happen compared to the oscillations we were just looking at? Okay, hopefully you said they should be more frequent, that the frequency should be higher and the period should be less. Because if you have a stronger spring force, the oscillation should occur more often, more frequently. So let's go ahead and start that. And indeed, they are. They are more frequent. Now it turns out they're not twice as frequent. They're actually square root of 2 times as frequent. That's not necessarily obvious to you until you really go through the mathematics, but they are indeed more frequent. And the time, that is the period of one oscillation, is indeed less. So notice that just the reverse is also true. If we decrease the spring constant, there's a smaller restoring force. And given that there's a smaller restoring force for the same initial displacement, the period is going to be longer. The frequency is going to be less frequent. In other words, it's not going to be as large of a force, so the restoring force being less, the oscillation is, again, the same amplitude, but less frequent and takes a longer time for the period. Okay, so hopefully this makes sense. Now what I want to do is I want to perform a very similar experiment, but just do it in the vertical, so we might have to, at times, take into account gravity, but we'll go ahead and do that. So what I have shown here is the most basic way we can look at a mass and a spring in the vertical direction by first ignoring the effects of gravity. So remember, we're ignoring the effects of gravity. So if you like, you can think about this as a horizontal tabletop that's frictionless, and we're just going to let this mass go back and forth, okay? Just sort of looking down on it. But we can be a little more quantitative, and we have a little more control here. So what I have here is a 100 gram mass, that's 0.100 kilograms in SI units. And notice that I have 2 identical springs, and those springs have the same spring constant, which can be set such that their unstretched length is what's shown here in blue. The resting position, that is the equilibrium position, is shown here in green when we hang this mass from the spring. And notice that this distance can be measured, and I can even bring in this movable line. Notice that this distance is, it's approximately 16 centimeters or so. And that displacement of 16 centimeters with this mass, you can equate the Hooke's law spring force in terms of its magnitude, k times x, equal to m times g, and you can solve for k. So that is to say, the weight force, mg, so that would be 0.1 kilograms times 9.8 meters per second squared on Earth, is equal to k times L, and L is 0.16 meters. So I've got the calculator out here. Let's see if we can calculate what this approximate spring constant is. So mg, that's going to be 0.1 times 9.8. So that should just be 0.98. And we're going to take that weight and divide by the mass to isolate the we're gonna take that weight and divide by the displacement of 0.16, that is 16 centimeters, and we'll get the Hooke's law spring constant in newtons per meter. So notice it's about 6.13 or so newtons per meter. That's not a very tight spring. Most spring constants are usually much larger than that, some of which, especially for like major springs like in your car, are several hundred newtons per meter. But anyway, Hooke's law spring constant will always be positive. Let's go ahead and see what a oscillation looks like for simple harmonic motion. So let's go ahead and displace this mass down a bit. And again, ignoring the effects of gravity, let's look at the simple harmonic motion. Okay, so that's what we'd expect. Let's bring this movable line in. And if I slow this down, I should be able to get the movable line to the place where this thing is below. Okay, so that's kind of the idea. And notice that here we have to be careful, because this is the center, the green line is the center of the 100 gram mass. So I think we need to get to the center of the 100 gram mass when it's completely elongated. So there we go. Notice that this right here, pay attention, this distance right here, from fully compressed to fully elongated, that's actually 2a, where a is the amplitude. So if you wanted the amplitude of the actual motion, you'd need to take half of this. So let's bring our ruler over here. So it looks like this is approximately, let's pause, this is approximately 0.17 meters, so 17 centimeters. So about half of that is 8.5 centimeters, or 0.085 meters is the amplitude. Hopefully you see how to solve for these things. What's interesting though is that if we go back to normal speed, we can also make some changes. Let's go ahead and stop this motion, okay? And let's go ahead and have it set up so that basically we have the motion so that we have not so much just a tighter spring. So let's do that at first. So instead of 1, 2, 3 notches here, let's go 4, 5, 6, okay, and stop this. Now notice that we're going to have a tighter spring. So let's go back to a similar elongation, and let's go ahead and see what the oscillation looks like. Okay, so it is more frequent. Okay, the period is indeed less. We saw this before. That should hopefully not be news to you. But now, instead of a larger spring constant, let's instead increase the mass. So let's go a 250 gram mass. Okay, now before I start this up, notice that the larger mass hangs lower. Given that it hangs lower, with the same spring constant, you would expect that. But given that it hangs lower, we should see that under any amplitude, remember the amplitude is irrelevant as it relates to the period and frequency. What do you think we should see? Higher frequency or lower frequency? And it turns out we should have lower frequency and we should have a longer period. That's because we have more mass to move. More mass to move means a greater inertia, so the period is less. Let's go ahead and compare to that 100 gram mass. Do you see that the 100 gram mass is more frequent, the period is smaller than the 250 gram mass, which the frequency is less and the period is longer for the 250 gram mass. Okay? So that's kind of the idea. So this is what it means to control the spring constant or the period, or sorry, the spring constant or the mass. By the way, let's just prove to ourselves that indeed amplitude is irrelevant. Let's put another 250 gram mass here, but let's give it a small amplitude oscillation. Okay, let me actually stop this one and give it, again, just a really small amplitude oscillation. Okay, so it's hard to see, but indeed the period is the same and the frequency is the same for both of these masses. Okay, so that's kind of the idea. By the way, you may ask, is there a way to get this 250 gram mass to be the same frequency as the 100 gram mass? Well, you could calculate that. The 100 gram mass is 2.5 times less massive, so we want to make the spring constant 2.5 times as much for this 250 gram mass. So here we're just going to have to sort of estimate it. But it turns out we can get these pretty close. Here we have a tighter, that is a stiffer spring, and a big mass. And then here we have a smaller mass with not as tight of a spring. So let's see if I can slow this down and try to get these things moving at the same time. Okay. So let's see if I've got it. Not exactly right. But again, you could calculate this so that you could get the frequency and the period to be exactly the same if you wanted to. Okay, now that we've really started to understand how this works, let's also add in the fact that in a vertical alignment, there is the force of gravity. So what is now shown here is basically the same experiment, but now we can show the gravity force, which is in red, the spring force, which is in blue, or we can look at the net force, which will be in black. We can look at the displacement from the natural length, that's what's shown here in green. The equilibrium point for the mass, that's the black line here. And again, we can bring out this movable line to kind of help us make some measurements. We can also bring out the ruler again. Okay, so here's the ruler if we need it. Okay, so notice when this spring hangs down, notice that from its unstretched length, notice that its displacement is below its unstretched length, that is its natural length. And notice that the displacement downward, so this is the total displacement from here to here, where the actual hook is. This displacement, which would be the same thing as the stretch, is take that times the Hooke's law spring constant. That should equal mg, which is the weight, because the weight down, that's this gravity, the red vector, and the Hooke's law spring force, that's the blue vector that's up, should be the same. In other words, this object should be in equilibrium. Again, this is often how real springs are estimated for their spring constant. Okay, so this is experimentally how you would do it. Let me just go ahead and show you that the oscillation should look like before, but notice that you'll see the forces vary and the displacement vary. Okay, do you see that the weight force, that is the gravity force, remains the same the whole time, but the Hooke's law spring force, let me slow this down, is smallest at the top and it's greatest at the bottom. Because I think the displacement, and by the way, this is different than when we had a mass on the horizontal table. Because when the mass was on the horizontal table, x was either positive or 0 or negative. Here, x is always positive. But since x is always positive, the Hooke's law spring force, when x is quite large, say like right around here, is greater than the weight. So the Hooke's law spring force brings us back towards equilibrium. When we are more compressed, the Hooke's law spring force is small, but the weight of course remains the same. X is still positive, but notice that we still move back towards equilibrium because gravity is the larger force in that case. So now indeed, let's put the net force on there. Notice the net force always brings us back toward equilibrium. Remember, the net force is the same thing as the sum of all the forces. In this case, it's the sum of the Hooke's law spring force and the weight, that is the gravity force. So you see how these forces work. Okay? Now, hopefully, if I make some changes here, these changes are not too surprising. Let me stop this. Let me go to a larger mass. Okay, so this thing should be elongated down further at first, okay? And let's go ahead and look at the forces. And let's move this movable line down. And let's give this a displacement. And let's do go. Notice that, again, the weight force is larger because we have a larger mass. So the Hooke's law spring force is larger because we have a larger initial displacement. But again, if I slow this down, you'll see that the Hooke's law spring force is greater than the weight force when we're below equilibrium. The Hooke's law spring force is less than the weight force when we're above equilibrium. And if we look at the net force is upward when we're below equilibrium, and the net force is downward when we're above equilibrium. I hope this makes sense. And what if we change this, let me stop, so that I had about the same size oscillation, but at a larger spring constant? So, larger spring constant, you should have greater spring force. So indeed, the net force is greater. And let's look at those individual forces. So now the Hooke's law spring force is indeed larger. It's really useful to slow this down because we know that when we have a larger Hooke's law spring force from the larger spring constant, the frequency should be higher and thus the period less. So this thing oscillates very frequently. But again, when we slow this down, the weight is larger than the spring force above equilibrium, and the spring force is larger than the weight below equilibrium. So now hopefully you really understand the kinematics and dynamics of simple harmonic motion. For springs, whether they're on a horizontal table, frictionless, or they are under the influence of gravity. By the way, we're assuming no friction, no damping, and no air resistance here. Okay, so those are all assumptions that are kind of built in. Let's now go one step further and let's talk about the energy, which I've mentioned before, but I want to nail it down in a little more detail. So the last thing I want to discuss for simple harmonic motion as it relates to springs only, I will show some other simple harmonic motion intuition videos here before too long, but I'd like to show the energy perspective. So what we're going to do here is we're going to plot kinetic energy in blue and elastic potential energy in this brownish red color, and the total energy is going to be in red. Now, by the way, down here the force will be in blue and the velocity will be in red, and we'll be able to set the initial position and the initial velocity of this mass, which is on a horizontal frictionless table where x is going to be positive to the right, negative to the left. And we're going to plot k and u here as a function of time. Here we're going to plot them as a function of x. And then here we're going to plot them as a bar graph, which can change in time. So let's first think about if we're just going to do a pure cosine function in terms of x versus t. I think that we should start off with all elastic potential energy at first. And that is indeed what we see. Notice that all the potential energy is the total energy to get started here. And notice that the elongation in x is reflective of the elastic potential energy. Notice the equations, 1/2 mv squared for kinetic energy, 1/2 kx squared for the elastic potential energy. Let's go ahead and start this up in a moment, but you should predict what each of these graphs should look like. Okay, so welcome back. I hope you paused the video. The potential energy should go down, the kinetic energy should go up, the kinetic energy should be maximum through equilibrium position. So this should be a sinusoidal wave, but in fact a sinusoidal wave, that's like a sine or a cosine squared. In fact, I think that the potential energy is going to be like a cosine squared wave, and then the kinetic energy is going to be like a sine squared wave. Why is that? Because sine is exactly pi over 2 radians out of phase with cosine. That is when potential energy becomes 0, kinetic energy becomes maximum. Furthermore, these should oscillate along, and they should both always be positive or 0. Notice that the potential energy should be sort of like a U-looking shape here as it relates to x when you plot potential energy as a function of x, because again, This is just a parabola, and when x is positive or negative, it's always positive potential energy, and the kinetic energy should be a downward facing parabola because, again, it's 0 at the ends but positive here. Okay? And these bar graphs should just oscillate along in time, but the potential is going to go down as the kinetic is going up. But the total energy should always remain the same. So let's start this. Look at what we have. We have a small amplitude oscillation. Indeed, the potential energy is like a cosine squared function. The kinetic energy is like a sine squared function. Notice the potential energy becomes maximum at x equals x max or x equals negative x max. The kinetic energy becomes maximum at x equals 0. That's when the velocity is maximum, at least the speed I should say. And notice that when the kinetic goes up, the potential goes down, and when the potential goes down, the kinetic goes up, but the total energy the entire time remains constant. If we reset this and just give it twice the initial elongation, so I can't go exactly twice, I think I can go to 75 centimeters, you're going to see about 4 times the potential energy. Why is that? Because there's an x squared in there. So if we make this elongation up to that 75, it's almost twice of what we had before. And notice we have almost twice the force, but we have almost 4 times the potential energy. So we're going to have 4 times the total energy. So these are going to be much larger amplitude oscillations, and there's going to be much more energy in the system. And in fact, the speed is quite a bit larger. Now you could calculate how much larger the speed is by equating 1/2 kx squared to 1/2 mv squared. The mass hasn't changed here, nor has the spring constant k. But again, this is what we mean by energetics of simple harmonic motion. So let's look at this in one more situation, and this time just let's do the vertical spring. So what I have shown here for our last experiment is the mass hanging from a spring, and there is gravity. There's Earth gravity on here, okay? So notice that we are going to look at various energies. Now notice there's gravitational potential energy above this height 0. Notice that if I was to move this mass up here, the gravitational potential energy would be larger because the height is just higher. But down here, notice that we have less gravitational potential energy, but more elastic potential energy because we're elongating the spring. So let's go ahead and release this and see what happens. By the way, we're going to ignore damping, ignore air resistance, no friction. So it's the oscillation like we had before. Okay, let's slow this down and see if we can understand this. So let's pause when we're near the top. So let's give it one more full oscillation where we pause near the top, and we're going to be all potential energy. Well, not all potential energy. There's going to be a little bit of elastic potential energy because the displacement is a little bit moved from the sort of natural length of the spring, the unstretched length, but the gravitational potential energy is largest here. When we move along, the elastic potential energy is growing at the expense of the gravitational potential energy. But notice the kinetic energy is maximum when we move through equilibrium. Notice that's because the speed is greatest there. Okay? So this is what we expected. Okay? So if you watch here, again, this is what our oscillation looks like. Now, what we can do is we can change this mass. We can make this more massive. Let's make it 200 grams as opposed to 100 grams. Okay? And then notice that 200 grams, we should have more mass in the system. So let me give this a greater oscillation. So we should have more mass in the system. Okay? So indeed, there is more mass in the system. And we should have, a greater elastic... we should have a greater gravitational potential energy because of mgh. We should have more kinetic energy because we have greater mass. But the elastic potential energy does not depend upon the mass, only depends upon how much we stretch it. So in fact, let's just stretch it a more modest amount. Okay, so notice that if we slow this down, we can see when we're going downward that we're losing gravitational potential energy but gaining elastic potential energy. Notice that when we move through the equilibrium position, the kinetic energy is maximum then. When we are fully compressed or fully elongated, the kinetic energy is 0. Notice the total energy remains constant the entire time. It's the sum of these three energies. We're assuming no damping, no energy losses to friction or anything like that. Okay? So, now that you understand this, I think you should understand simple harmonic motion. I want to thank you all very much for watching this video. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social networks. And I want to thank you for watching High Peak Education. I will see you in the next video.